In previous video, we have studied the electrical properties of semiconductors. Now we will see the different numericals which have appeared from this topic in GATE examination, one by one. So, in electrical properties of semiconductors, we studied conductivity, mobility and drift velocity. We have also studied the effect of temperature on conductivity of semiconductors. We have not seen this 4-point pro method of measurement of sheet resistance. We will discuss it later. Now, the first question, an N-type silicon bar 0.1 centimeter long and 100 micrometers square in cross-sectional area has a majority carrier concentration of 5 into 10 raised to power 20 per meter cube, and the carrier mobility is 0.13 meter square per volt second at 300 K. If the charge of electron is 1.6 into 10 power minus 19 coulomb, then resistance of the bar is, we have to find the resistance of the bar. So what we are given? We are given length of the bar, we are given cross-sectional area of the bar, we are given majority carrier concentration and carrier mobility. So the conductivity of extrinsic semiconductors we have just seen, that is sigma equal to E into P mu P plus N mu N. We have already seen what is this. P concentration of holes in valence band, mu P is mobility of holes, and N is concentration of electrons and mu N is mobility of electrons. For N-type semiconductors, here we are assuming, this is given, we are assuming that it is N-type material with N much greater than P. Rather, it is mentioned it is N-type semiconductor. So for N-type semiconductors, the electrons are majority carriers, holes are minority carriers, and concentration of electrons is much greater than holes. So sigma is approximately equal to Ne into mu P. So this factor is eliminated, just eliminated because of the large value of N. So we have by putting the values of Ne and mu N, we get the conductivity that is equal to 10.4. So resistivity becomes 1 by rho, so that is 0.096 ohm meter. So resistance of the bar is R equal to rho L by A. So we are given length, we are given cross section, so we get resistance of the bar here. And this is the reference given in the solution. I give normally reference for every question. Then let us see the next question. This is the next question. The resistivity of a uniformly doped N-type silicon sample is 0.5 ohm centimeter. If electron mobility mu N is 1250 centimeter square per volt second, the charge of electron is 1.6 into 10 power minus 19 coulomb. The donor impurity concentration in the sample is, we are given resistivity, but we know the conductivity for extrinsic semiconductors. This is N-type material, so this becomes sigma is approximately N into mu N. Then we know the concentration, N is equal to sigma by E mu N. So sigma is 1 by rho, so it is replaced by rho. So we get the concentration of the electrons. Since concentration of the electron is almost equal to the donor concentration, therefore we get the donor concentration from this equation. This is the reference. Then let us see the next question. Here a silicon sample A is doped with 10 to the power 18 atoms per centimeter cube of boron. Boron is basically acceptor impurity, that is from third group of the table. Another sample B is identical, is of identical dimensions, is doped with 10 to the power 18 atoms per centimeter cube of phosphorus. Phosphorus is basically the N-type impurity. So the ratio of electron to hole mobility is 3, mu N upon mu P is given. The ratio of conductivity of the sample A to B is, so we are given acceptor concentration, we are given donor concentration, we are given mu N upon mu P equal to 3. So conductivity of extrinsic semiconductors is given this. So for P-type material, P is much greater than N. So we take concentration of holes approximately equal to the acceptor concentration. So sigma is equal to NaE mu P. And for N-type materials, concentration of electrons is much greater than holes. Therefore, N is approximately equal to Nd. So now sigma B will be equal to NdE mu n. So just by dividing this equation by this, we get the ratio, and that is 1/3. This is the reference. Now let us see the next question. A heavily doped N-type semiconductor has following data. That is, whole electron mobility ratio is this, that is 0.4. The doping concentration is 4.2 into 10 to the power 8 atoms per meter cube. The intrinsic concentration is 1.5 into 10 to the power 4 atoms per meter cube. We have to find the ratio of conductance of N-type semiconductor to that of intrinsic semiconductor of same material at the same temperature. So we are given what donor concentration, we are given intrinsic concentration, ratio of mu p to mu n is given, ratio of mobility of holes to electrons is given, that is this. So we know the conductivity, that is sigma equal to n for intrinsic semiconductor, that is sigma I equal to ni e mu p plus mu n. So we get, you are already given mu relationship between mu n and mu p, so we get 1.4 into ni e mu n. Conductivity of extrinsic semiconductor, that is sigma A equal to E P mu P plus N mu N. So for N-type material, N is much greater than P, so N is approximately donor concentration. So that is sigma N is equal to Nd into E mu N. So we get the ratio of extrinsic semiconductor to intrinsic semiconductor conductivity is this. This is the ratio. We divide this by this relationship, so that comes out to be this much. So, and this is your reference. Now let us see the next question. In figure, log ln, that is natural log ln rho I is plotted as a function of 1/t, where rho I is the, that is rho I is the intrinsic resistivity of silicon, T is temperature, and plot is almost linear. You can see that is a relationship, that is plot between ln rho I and 1/t. The slope of line can be used to estimate. You have to see this, the estimate, we have to see what is this slope representing. So we know the conductivity of intrinsic semiconductor, that is this. Intrinsic concentration we know, the formula we have seen. So where A naught is a constant, T is temperature in Kelvin, and Eg naught is band gap at 0K. So by putting this Ni in this equation, we get this relationship, and we know intrinsic resistivity is 1/sigma I, so rho I is this much. So now just by putting that relationship here, we get this, taking log on natural log on both sides, you get ln rho I equal to this. So finally this is e raised to power Eg naught divided by 2 kT. So you are taking natural log, so this comes out to be in front of ln. Ln E is of course 1, and this second part, this is the second part. So this is nothing but equation of a straight line, y is equal to mx plus c. Y is y-axis of the curve, that curve we talked about, and 1/t is x-axis, so 1/t is x-axis. So y is ln rho I, m is slope, and x is 1/t. So that equation, if you draw the curve between ln rho I and 1/t, so this is representing the slope. So it means that curve can be used, so that can be used to find the slope of the straight line between, or slope of the line. You can, what I mean to say is, you can use this curve, to determine the slope. It is given, it can be used to the slope of this curve can be used to determine band gap energy. How band gap energy? Because the slope is function of band gap. Here slope is function of band gap. That means the slope of the given curve can be used to determine the band gap energy of the intrinsic semiconductor. So now let us see the next question. A piece of silicon is doped uniformly with phosphorus with a doping concentration of 10 to the power 16 per centimeter cube. The expected value of mobility versus doping concentration for silicon assuming full dopant ionization is given below. That is given variation mobility versus doping. The charge of electron is this much. Conductivity of the silicon sample at 300K is, you have to find the conductivity. So you know the expression of the conductivity. The point here is we have to estimate the mobility from the given curve. The doping concentration is given. So from the given curve we have to find the we have to find the mobility of electrons. You can see, please see this curve at a concentration of how much? You are given concentration of 10 to the power 16. So at a concentration of 10 to the power 16, mobility of electrons comes out to be how much? 1200 centimeter square per volt second. So by putting this mobility in and donor concentration in this expression, we get the conductivity here. So now let us see the next question. A DC voltage of 10 volt is applied across an N-type silicon bar having rectangular cross-section and length of 1 centimeter as shown in the figure. The donor doping concentration ND and mobility of electrons are 10 to the power 16 per centimeter cube and 1000 centimeter square per volt second respectively. The average time taken by electron to move from one end to the another end of bar. You have to find the time taken to cross the length of the bar. So we are given donor concentration, we are given mobility of electrons, length of the bar is given. So if voltage and length is given, you can find the electric field inside the bar. So drift velocity of the electrons is given by Vd is equal to mu n into E. We have seen this expression. So just by putting this, we get the drift velocity of the electrons inside the bar. And we know, if you know the drift velocity and length is given, so I can calculate the time taken by the electron to move from one end to another end, that is L upon Vd. So that comes out to be 10 to the power minus 4 second or 100 microseconds. Reference for this is Streetman and Banerjee 7th edition. So this is the second book I have referred for this topic, that is Solid State Electronics Devices by Streetman and Banerjee. Now let us see the next question. Under high electric fields in semiconductors with increase in electric field intensity, what is the effect on the drift velocity and mobility? So let us see. Drift velocity Vd is mu into E. We know mu is constant for E less than 10 to the power 3 volt second. I have given you the variation of mu versus E. So by putting this relationship, mu is given for this range, so we get Vd is proportional to E because it was constant here. So Vd comes out to be proportional to E. Then for this range, it comes out to be proportional to root of E, and for E greater than 10 to the power 4 volt per second, Vd comes out to be constant. So answer are A and C, that is mobility of the charge carriers decreases with increase in field. You can see from these relations. And the velocity of charge carriers saturates. High electric field we are considering E greater than 10 to the power 4 volt per second. So this is inversely proportional, but this is becoming constant. That is why I have given option A and C. And reference for this is Millman Helkias. This is the reference for the question. So now the next question, let us see. An N-type silicon sample having electron mobility mu n equal to twice the mobility of holes is subjected to a steady illumination such that the electron concentration doubles from its equilibrium value. As a result of conductivity of the sample increases by a factor of use. You have to see the effect on the conductivity when electron mobility is twice the mobility of holes. So this is what you have. For extrinsic semiconductor, it is N type, so I am taking sigma approximately equal to N into mu. If illumination is applied, it will result into generation of electron hole pairs. If the concentration of electrons is doubled, which increases from N to 2N, then concentration of holes will also become P to P plus N. What I mean to say, when you illuminate the material, suppose what is given to us, we are given illumination is resulting into doubling of concentration of electrons. If illumination is resulting into doubling of concentration of electrons, so that means N is becoming N to 2N, but holes will become what? P to P plus N. Why? Because generation of every electron result into generation of one more hole. So if electrons are double from n to n, then holes will become from p to p plus n. Same number of holes will be generated. So the conductivity will be, so replace concentration of holes from p to p plus n and replace n by 2n. So you get this result. But approximate result. So mu n is equal to 2 mu p, that is given to us. So by putting this relationship into this, we get sigma equal to 2.5 into sigma. So conductivity will be increased by a factor of 2.5, and this is the reference for the formula used. So now let us see the next question. A small concentration of magnetic carriers is injected into homogeneous semiconductor crystal at a point. An electric field of 10 volt per centimeter is applied across the crystal, and this moves the minority carriers at a distance of 1 centimeter in 20 microseconds. The mobility of the charge carriers is, you are given the charge carriers are moving 1 centimeter in 20 microseconds, so I can find the velocity. So this is nothing but drift velocity. Why? When electron moves under the influence of electric field, that is drift velocity. So Vd is this. We are able to calculate Vd by using these two values, and we are given electric field. So mu will be Vd upon E. So by putting this value, I get the mobility of the charge carriers, and this is the reference for the formula used. So then let us see the next question. Drift velocity of electrons in silicon is proportional to electric field for all the values. That is not a fact. I have given all the possible variations by using this. So answer is D. The drift velocity of electrons increases linearly with electric field at low values and gradually saturates at higher values. You can see initially it is increasing, then it is saturating when electric field is changing from 10 to the power 3 volt per centimeter to 10 to the power 4 volt per centimeter. So it means velocity first increases and then saturates. I have drawn the that variation of Vd with respect to E in my video. So let us see the next question. A silicon sample is uniformly doped with donor type impurity with concentration of this is given to you. The electron and hole mobility in the sample are this much. Assuming complete ionization of impurity, the charge of the electron is resistivity. You have to calculate, and we know what is conductivity. This is semiconductor as much greater than this, so you have to find the resistivity, and we know what is resistivity. Resistivity is 1 by conductivity, and we get this much value 0.52, and this was the option given to you. This is the reference for the formula used. So this is all about the all questions which have appeared in GATE from the electrical properties of semiconductors. So my method will be like this only. First I will take the lecture. So my first video will be on the lecture, and my next video, following video, will be on the questions which have appeared in the exam. That will be in the separate video. Reason being, otherwise video becomes very lengthy and you lose your interest. So just wait for my next video. And one more request, if you are liking my lectures, videos, and solution of the questions, you can see I have given even the reference in every question. So please like and subscribe the channel and recommend it to your friends, so that I get motivation. When number of viewers increases, I will be definitely motivating myself and giving more and more output. Thank you very much.